Good evening and welcome to MP Live Lessons. This is a delayed lesson due to a few circumstances. Physics paper 2 will be delayed as well by one day, so it will be released on Friday night. But this is chemistry paper 2 right now. This is not until actually the last week of GCSE exams, really, so you should only be watching this like a week or two beforehand, but here I am right now. So what we're going to start off with is Unit 6, Rates of Reaction. So we're going to start off with the basics of this, so collision theory. So this is actually a link to Paper 1, Topic 5 of Energy Changes. So what must happen for a reaction to take place? So reactants need to have enough energy, so particles, so the reactants must have enough energy. And to react, they do this by colliding. Now, what's meant by activation energy in terms of bonds? So if you remember from Unit 5, you did some of these bond energy calculations. So you calculated the bond energies of reactants. So was the energy needed to break the bonds of reactants. And that means we have a new definition for activation energy. So in terms of collision, so it's the minimum amount of energy needed for particles to collide to react. And you should usually get this definition down. This is often worth 2 marks. Now in this unit, you'll also look at the rate of reaction. So in a reaction, you have reactants reacting together to form products. So a rate is how fast something happens. So the rate of reaction can be measured in two ways. Either we can look at the amount of reactant used over a certain period of time, or we can look at the amount of a product made over a given time. Now, each of these would have different units, and how can you measure each of them? So this would be, for example, the reactant used or the product made, so anything to do with chemicals. So you can measure this in two ways, either its mass, which is in grams, or its volume. And time is often measured in seconds. So your rate would be your unit for the mass or volume, so the unit to measure your chemical, divided by or slash unit for time, which is usually seconds, but they could put minutes. For example, you could have one such as grams per second. That's one example, but it always depends on the question. Now, you can measure these by, for example, the chemical produced or made. If it's a gas, you can often measure it with a measuring cylinder or a gas syringe. Or what you could really do if you, for any of these, if it's the mass, you just use a top pan balance. Now the mass can increase or decrease depending on the reaction. Now, you could also note that the rate of reaction can be how frequent the reactant particles collide together. This can actually help us explain how the rate of reaction can change depending on a condition. So these tend to be 3 to 4 mark questions, so these are quite important. For example, we could see that the concentration can affect the rate of reaction. This is usually for solutions or liquids. This could also be the same for pressure in gases. So what's meant by concentration? So this is the amount of reactant, or mass, as they prefer you to say, a reactant per unit of volume. So a higher concentration means more mass of a reactant per unit of volume. So that just means there's more of that reactant there. For example, if you've got a high concentration of acid, there'll be more acid particles. That's acid there is a reactant. Therefore, there will be more frequent, they like you to say this, more frequent collisions between reactant particles. So therefore, as you increase the concentration, the rate of reaction increases. Another factor you need to look at is the surface area, and this usually applies to solids. So usually, one good example could be a very small strip of a metal, let's say that's magnesium. How could you change the surface area of this reactant? You can either cut it up into smaller pieces, perhaps, or you could break it down into a powder. This increases the surface area. So a higher surface area means more particles or more reactant particles are exposed at the surface. So more reactant particles are exposed at the surface. So for example, if I compare it to the strip of magnesium, you'll have little dots of this magnesium instead. So other reactant particles can react from pretty much any side. It's more exposed. Therefore, there's more frequent, again, collisions between reactant particles. So that means the rate of reaction goes up if you increase the surface area. Two more factors you need to look at is temperature. So this is a link to physics actually. So at higher temperatures, the particles will move faster. With more kinetic energy. So again, that means there's more frequent collisions between reactant particles. But also you can say something else for temperature. You could even say that these collisions themselves are more energetic. So the collisions are more energetic. You could even say, if you want to show off, is that a higher proportion of collisions have more energy than the activation energy. So like above the activation energy. So more of those collisions that actually happen will actually happen above the activation energy. So more. So overall, if you increase the temperature, the particles move a lot faster and with more energy. So this causes more frequent collisions. They'll collide more often. And also those collisions themselves, since they're moving fast, they will collide with more energy. So this increases the factor quite a lot. And the last factor is a catalyst. Now, this is a link to Unit 5 once again, so we're going to draw a reaction profile for an exothermic reaction. We're going to fully label it. Now we're going to draw our axes again. So we have energy on the left, and we have the progress of reaction on the x-axis. So since this is an exothermic reaction, energy is transferred to the surroundings. Our reactant line is higher than the product's line. It will jump up and go down. This little bit that goes from the reactant line to the top of the curve, this is activation energy. And this, remember, is the minimum amount of energy needed for particles to collide and break their bonds. And this, from the reactant to product line, it's an arrow going down, is the overall energy change. Now, what a catalyst does is that they lower the activation energy. So what happens is if I draw a new line in green, they will lower the activation energy, so it will rise a bit less, but still have the same overall energy change. So it rises less, so that means less energy is needed for the particles to collide, and that means more free, like a collision will be above that activation energy, so there's more successful collisions. And this can allow catalysts like to make reactions happen at lower temperatures because lower temperatures will have less energy but still get the reaction done because the activation energy is lowered. Now, this is a common practical for rates of reaction. So this would be like a required practical. So one of them could be measuring the volume of gas over a certain period of time. So in this example, we'll use the reaction between magnesium and hydrochloric acid. As you know from paper 1, this will produce a salt and hydrogen gas. And just remember, this works for any metal that's more reactive than hydrogen, and any acid really. So the factor, for example, will change is the concentration of acid. Now, how would we make this a valid fair test? So we'd have to keep the other factors constant, like the surface area, the temperature, and the mass of magnesium used. So the mass of magnesium used is pretty easy. Just you've got to weigh it out on a top hand balance. The others aren't so much. With the surface area, you have to keep them the same. For example, use only a strip of magnesium or a powder. And lastly, with temperature, we can either keep it in a water bath, like a test tube, use a test tube in a water bath, and we can also check the temperature at the start of the reaction. So for example, we can keep this test tube in a water bath heated at, let's say, 30 degrees Celsius. So it's the same each time. Now, for the experiment, how could we measure the rate of reaction? So we were producing a gas, and I hinted at this right at the start. What equipment could we use? We would use a gas syringe. This would be for small volumes often. But if it's a lot of gas being produced, you should use a measuring cylinder. Yes, it's used for liquids, but what you do is you'll have some container of, let's say, water. Then you'll put your actual measuring cylinder upside down, and the gas gets collected into here. And what happens is that water is displaced and it will get pushed out of the measuring cylinder. Now, to measure the actual rate, remember we needed the formula, which was the amount of products made, which was with this gas syringe or measuring cylinder divided by time. So that means we need to use a stopwatch. Now, the method for this would be as follows. So remember, we're seeing how the concentration will affect the rate of reaction. And we're going to use a reaction that produces a gas, hydrogen. So if the reaction happens faster, more gas is produced in a certain amount of time. So here's the method. First, we measure out 20 cubic centimeters of hydrochloric acid with a concentration of 0.1 moles per cubic decimeter. So we are keeping the concentration the same. We use this, like the set volume as well, with a measuring cylinder, and then we put this into a boiling tube. Now we wait 4 minutes to let the acid reach the room's temperature. So that's usually around 20 degrees. So that means we're keeping the temperature constant. Then we measure and record its starting temperature, just to check it's the same temperature each time. Let's say 20 degrees or 22. Now, on the top band balance, we're going to measure out or weigh out 2.5 grams of a single strip of magnesium. And in each experiment, we're just going to use the same again. So the surface area is going to be the same. Then we add this to the acid and we immediately attach a bung to the boiling tube so that we can collect the gas into an empty gas syringe. And we start a stopwatch at the same time. So what we have is our boiling tube. So once we put the magnesium in, like this little wire here, we're going to attach it off and seal it with this bung, which then connects to a gas syringe like this. And then every 30 seconds, we're going to measure and record the volume of gas in the syringe for a total of 5 minutes. Now, finally, we repeat steps 1 to 5, so we measure out the acid, put it in, wait for it to reach room temperature, then we add the magnesium, then we seal the top and collect the gas and measure the volume of gas every 30 seconds for a total of 5 minutes. So we keep repeating all that with different concentrations of acid, actually. So ignore what I said. So you have to suggest some values like 0.2, 0.4, 0.6, 0.8, and 1. Now, sometimes you may not be able to measure the amount of product made. You could measure it in a different way, or the rate of reaction in a different way. This is through something else, such as a visual change, such as a change in color. And that's the second variant of this practical. So this is where we look down a flask and we wait for a cross to disappear. So in this reaction, we're going to use sodium thiosulfate and hydrochloric acid. Now this produces a salt, water, a smelly gas, which is sulfur dioxide, and sulfur. Now this sulfur isn't soluble and it has a unique almost white or yellow color, and that's what we call a precipitate. We can see it in water and it turns it or makes it impure and no longer makes it clear, so we can't see through it. So like the other variant of the practical, we'll, let's say, change the concentration of acid and keep the other variables the same. Now, measuring the rate of reaction is a bit harder because we can easily see a product is being made, but we can't exactly measure it. Let's say its mass. So what we have to do instead is we have to peer down the flask and we need to see when the solution becomes opaque. So we have our flask. We fill this up. Eventually it's going to become opaque so we can't see through it. And what we have beneath is a little sheet of paper just with a big X on it. And when we can't see that X anymore, it's opaque. So this tells us the reaction is pretty much finished and we only measure the time taken. And the faster rate of reaction this time is a shorter time. Now, we have a similar method again, but we're going to change bits of the method. So again, we measure a set volume of hydrochloric acid with this concentration, 0.1 moles per cubic decimeter, into a conical flask, and we use a measuring cylinder to measure out this volume. Now, what we do is we place this flask over a white tile and a piece of paper with a larger black cross, so we make it easy for the dark cross to be seen until it isn't. Now, again, we wait 4 minutes to let the acid reach a room temperature, or again, you could use something else. Then what we do is we add a set vol mass of sodium thiosulfate, like 2.5 grams, measured in the top pan balance. And what we do after we've added it into the flask, we start swirling the flask and we start a stopwatch. Now we keep swirling the flask until we don't see the black cross anymore. So we have to continuously look down the flask. And when you don't see the cross anymore, we stop the timer or the stopwatch. And we record this. And we repeat all this with different concentrations of hydrochloric acid each time. So for example, with 0.2, 0.4, 0.6, 0.8, and 1 moles per cubic decimeter. Next on this unit are reversible reactions. So for a while, you've been dealing with irreversible reactions. So these form reactants to products. So they go in one direction, shown with the arrow. So the reactants react together and form products. These are irreversible because they can't go in reverse. However, some reactants are reversible. The reactants make products, and the products can make the original reactants again. Now, from Unit C5, energy changes from paper 1, you know that reactions can transfer energy or to or from the surroundings. So energy to the surroundings is released, that's exothermic, and energy from the surroundings, taking it in, is endothermic. For a reversible reaction, the energy transfer changes when you go in the opposite direction. For example, if the forward reaction, which is left to right, if that is exothermic, the other way around, from right to left, or the backwards reaction, this is endothermic. Now, as a result, since you have reversible reactions, you have a point called equilibrium. Equilibrium, if you're familiar with the word, is where something is balanced. So this only happens first in a closed system. So reactions, reversible ones, in a closed system. This is where particles or any reactants or nothing can get in or out. Now, equilibrium is reached if the forward and backward reaction happen at the same rate. So at the same time, reactants make the products and the products make reactants. So the mass of each doesn't change. So that means at some point in the flask, you could perhaps measure out what percentage are like the reactants and what percentage are the products. For example, it could be 60% reactants, 40% products in the closed system. And this depends on the conditions. It doesn't have to be, let's say, 50-50, it could be 60-40, as I said. It could be even, let's say, something different. Again, it depends on the conditions. Now, of a higher tier only, you need to know the equilibrium can change if the conditions change. This is where we bring in the name dynamic equilibrium and the chap Le Chatelier. So he came up with this principle, Le Chatelier's principle. So if a closed system is in equilibrium, so that's where the forward and backward reactions happen at the same time. So this is the forward reaction. This is the backward one. So if they're happening at the same rate, they're in equilibrium. However, if we change a condition, the system will counteract and do the opposite to change. So again, if a condition changes, the system will try and counteract this, and then eventually a new equilibrium is formed or found. For example, let's say the closed system is in equilibrium, but then we increase the temperature. The system will counteract by decreasing the temperature. Now, I've got an example at the bottom here, which is familiar to those who take triple science. So nitrogen reacts with hydrogen to form ammonia. Now, one factor you need to know that affects equilibrium is temperature. So I'm going to tell you right now that the forward reaction from left to right is exothermic. Now, explain what happens to the equilibrium if the temperature increases. Before we do this, we need to label it. So the forward reaction is exothermic. That means the backward reaction is endothermic. So forward is exo, backwards is endothermic. So if the temperature increases, the system counteracts. By decreasing the temperature. Now to decrease the temperature, what the system does is the endothermic reaction will happen much faster. So the endothermic reaction happens much faster because endothermic reactions result in the temperature decrease. So that's the backward reaction, going from right to left. As a result, we can say that the equilibrium shifts to the left. So that means if we increase the temperature, the system will counteract by decreasing the temperature by making the endothermic reaction, the reaction going from right to left, happen much faster. That will try and decrease the temperature, and as a result, the equilibrium shifts left. So more of the products on the right will then split up into the original reactants on the left. Now, the opposite happens if the temperature decreases. So the system will counteract again by increasing the temperature. This means the exothermic reaction happens faster. And the equilibrium shifts this time to the right. Now, a factor you need to know that affects the equilibrium is the concentration, or just how much of a reactant there is. So what happens if the concentration of, let's say, the reactants decrease? So the system counteracts, and it wants to increase the concentration of reactants, so increase the number of reactants. And this is done by, to produce more reactants, so more of these products on the right here go back and instead go back into their reactants. So that means the backwards reaction happens faster, which produces more of the reactants. That means the equilibrium shifts to the left. Whereas the opposite happens if we decrease the number of products or the amount of products. So the system will counteract by increasing the number of products. So that means the forwards reaction from left to right happens faster to produce more of those products. That means the equilibrium shifts to the right. Now, lastly, we have another factor, which is pressure. So notice that these particles here are all gases, or reactants and products are all gases. Now, let's say if the pressure decreases, the system counteracts by increasing the pressure. However, to increase the pressure, we need more particles or more molecules. So that means, so if we count them, so N2 is a particle itself, so that's 1. H2 is just a particle by itself, but we've got 3 of them. And on the right, so we've got NH3 is a particle in itself, so there's 2 lots of them, so there's 2 here. So in total, there are 4 on the left, 2 on the right. So if we want to increase the pressure again, we need to produce more molecules, and this means the backward reaction happens much faster to produce more molecules. That will produce more particles to exert a force, and that means a higher pressure. So that means the equilibrium shifts to the left. So that means eventually we reach a new equilibrium. So that's something I forgot to say on those previous two slides. This shifting keeps happening until a new equilibrium is reached. Now the reverse happens if the pressure increases. System counteracts by decreasing the pressure and it shifts to the side with fewer molecules. So the forward reaction happens faster and the equilibrium will therefore shift to the right. Eventually, a new equilibrium is reached. Next is a slightly shorter unit for this year is organic chemistry. First off, we start with crude oil. So what is it? So these are the remains of like organisms such as plankton, trees, dead sea animals that have been compressed over millions of years. And that's how it's actually formed. Now this crude oil contains different like fractions. So what's meant by fraction is um, hydrocarbons with similar lengths of carbon atoms, which have similar properties. And as a note, crude oil contains many fractions. So different variety or wide variety of hydrocarbons, all of different lengths. Now, we have some general properties of these hydrocarbons. So we already know that crude oil is made up of different fractions. So ones with similar chain lengths of carbon atoms, so big range. They'll have similar properties such as boiling points. And we have to separate these fractions apart because we can't just use crude oil on its own. These fractions will have different useful properties. So that means each fraction is useful for a specific purpose, such as fuels, tarmac, and so on. Now each fraction has different properties, such as its boiling point. So this boiling point will increase with longer chains of carbon atoms. Now this is also a link to paper 1. So the boiling points will increase as the carbon like in atom chain like becomes longer because longer chains of carbon atoms will have stronger intermolecular forces of attraction which have or need more energy to break or overcome. As a result, this affects the volatility. So this links to the boiling point. So this is how easy it is for the hydrocarbon to become a gas. So that means a lower boiling point will make the hydrocarbon more volatile, easier to perhaps store. Those are like gases perhaps like for camping stoves, like butane, propane. Next is the flammability. Shorter hydrocarbons tend to be more flammable. This is probably because it has a shorter chain, fewer bonds because there's fewer bonds between fewer carbon atoms, and that means you need less energy to break those bonds and react. So this is why camping stoves tend to use shorter hydrocarbons, again, like propane and butane. And lastly is viscosity. The longer the hydrocarbon it is, the more viscous or thicker the hydrocarbon liquid runs. So that's why you have long hydrocarbon fractions, such as those used for like tarmac, like bitumen. Those will flow really slowly. That's one example. That's used to produce tarmac for roads, produce tar, and so on. It needs to stay solid at high temperatures because it has a long chain of hydrocarbons. Now, to separate all these hydrocarbons or fractions, we need to use fractional distillation. Now, since we are separating liquids with a range of boiling points, we use this process, and this will use a big fractionating column, which has varying temperatures. So this is a very tall cylinder or column, if you like. That's where the gas is fed through, and then each fraction is collected at different levels, and you'll see why. This is often, let's say, a high mark question, like 4 marks, to describe how fractional distillation separates crude oil into different fractions at different heights. First, you need to say is that the crude oil is heated to around 450 degrees Celsius, so all the fractions turn into a gas. Then the fractions enter the fractionating column at the bottom, and they start to rise to the top, where the temperature starts to decrease. Now, you should know that each fraction has different lengths of hydrocarbons, and they will have different boiling points. That means each fraction will condense into a liquid at different heights because it's hotter at the bottom of the column and cooler at the top. As a big note, if you forget anything, just remember each fraction has different boiling points and condenses at different temperatures. Now, one kind of hydrocarbon you need to know about are the alkanes. So these are most of the hydrocarbon compounds that you find in crude oil. These are chains of carbon atoms of varying lengths saturated with hydrogen atoms, and all the carbon atoms are bonded by single covalent bonds. And remember, each carbon atom has 4 electrons on their outer shell. That means they can have a maximum of 4 covalent bonds. They can have a maximum of 4 electrons on their outer shell to share, whereas hydrogen only has 1. For example, if we draw out one of the hydrocarbons, let's say we have two carbon atoms like this, then we draw hydrogen atoms all around like this, which can take a long time. Then we draw lines in between to show the covalent bonds. And notice there are only single lines between the C's and the H's, or the C's and the C's. That represents the single covalent bond. You'll need to memorize the name, structure, and formula of the first 4 alkanes. So these are the compounds that have 1, 2, 3, and 4 carbon atoms, or 1 to 4 carbon atoms long. First is methane, with the formula CH4. So it'll have 1 carbon atom in the middle, not bonded to anything else, but there's going to be hydrogen atoms all around it, all bonded together by single covalent bonds. Next is ethane. This will have 2 carbon atoms and 6 hydrogen atoms all around it. This is what we actually drew. And remember that these diagrams are called displayed ones. The third one you need to know about is propane, which has 3 carbon atoms and 8 hydrogen all around, so in a similar pattern. And lastly, butane, with 4 carbon atoms and 10 hydrogen atoms all around, surrounding the carbon atoms. So if we keep doing this, we actually see a pattern. The general formula for an alkane is CnH2n plus 2. So N is like the number of carbon atoms. For example, if we had, let's say, decane, which has 10 carbon atoms, its formula is obviously your number of carbon atoms, and then that's N is 10, then your H, we double it and add 2. So we double it, which gets us 20, and then add 2, so 22. So there are 22 hydrogen atoms in decane. One other thing you need to know about this organic chemistry unit is cracking and alkenes, very briefly. So cracking, by the name suggests, involves cracking or breaking down longer chains of hydrocarbons into shorter ones. Why is this done? So this is done to meet the high demand for the shorter chains because they're more useful. They're actually more flammable, so they make better fuels. They're more volatile. They're less viscous, so they can run much easier and are easier to store. However, in naturally occurring crude oil, there isn't enough of these shorter chains to meet the demand of what we use for these shorter chains. So there isn't enough of these shorter chain hydrocarbons to give us what we need. That means we need to break these longer hydrocarbons, which we don't use as much, into shorter ones, which will sustain the supply for it. Now, let's say we break down quite a large-ish hydrocarbon that has 8 carbon atoms and 18 hydrogen atoms into two new hydrocarbons. Now, if we remember the general formula for alkanes, which is CnH2n plus 2, we can see that these two here are alkanes, but this one isn't. There's twice as many hydrogen atoms, nothing like with the plus 2. That means we've found a new type of hydrocarbon, which has a general formula CnH2n. This is an alkene. So these have properties similar to a alkane, but are unsaturated hydrocarbons, and they have a double covalent bond across 2 carbon atoms. For example, in this case, we'll have 3 carbon atoms like this, but there will be a double bond across one of them. It doesn't matter where you put the double bond when you're drawing out the displayed formula. Whereas everything else are single bonds, and remember that carbon atoms have a maximum of 4 covalent bonds, or lines, if you like. So that means we can only put 6 hydrogen atoms in this way. Like this. And we can see there's loads of gaps because it's unsaturated. So unsaturated means not the maximum number of hydrogen atoms bonded. So we don't have the maximum number of hydrogen atoms possible that bond to these carbon atoms. So there's gaps left there. Now quickly take a quick screenshot of this displayed formula. And there's one last thing to show about alkenes. You can test for the presence of alkenes using something you're familiar with, which is bromine water. So bromine water is initially orange, but if alkanes are present, it turns the bromine water colorless. Now, for cracking, since this is an industrial process, you may need to know roughly the conditions for it. First, you just need to know it's catalytic, like two different types of cracking. First is catalytic cracking. So this uses, as the name suggests, a catalyst. And the other two conditions for catalytic cracking is a high pressure, which is about 20 atmospheres, which you don't need to know, and high temperature, about 550 degrees. You should roughly know this. As you know, it already uses a catalyst. The other process for cracking is steam cracking. This also uses a high pressure, but much more than catalytic cracking. It also uses a higher temperature, but still it's quite high, 800 degrees Celsius. Instead of a catalyst, it uses steam. That's the end of organic chemistry, and now we're moving on to chemical analysis, Unit 8. Now, for combined science, you'll need to remember about these purity of substances, something you may have done a long time ago. So you need to know what's meant by a pure substance and a mixture and the formulation. So a pure substance is literally only one substance. This could be only one element or only one compound. One example could just be pure water, where there's only water molecules. Now, a mixture contains more than one substances. And a good example is air, because it contains nitrogen, oxygen, carbon dioxide, and even water vapor. Lastly, a formulation is also a mixture, but with a useful purpose. One example could be the E10 fuel. So for example, this has 10% ethanol, so that counts as a mixture. Another good example could be paint. Another even good, better example could be baby formula. So that's like the powder you put in. Now, for combined science, they have a required practical, which is chromatography. Now, you may be familiar with other ways to separate substances, like from paper one, such as filtration, crystallization, distillation, and so on. Now, chromatography separates liquids with similar boiling points and identify common substances in mixtures as well. One common example is with inks or paints. So what could the common substances be? So these would often be colored dyes. Now, I'm going to drop the setup used for chromatography, and this has many important details. So first, what we have is our chromatography paper. So this is a big sheet that we have. Then, on this little special piece of paper, we draw a starting line at the bottom, as well as some crosses. So These starting lines and the crosses, these are done in pencil, and we'll see why. The X's are for like the ink we want to investigate. So what we do is we put the ink on those X's there, sample it in the middle, and then we carry out the experiment. Other things we need is a beaker to put it in, then you'll need a solvent as well. In other words, this is just a liquid. And ideally, you'd also have a little lid as well to stop any of the solvent evaporating. Now notice as well, the liquid shouldn't be filled too much. There shouldn't be too much liquid, so that the starting line must be above the liquid. Now, what happens after this is that, let's say we put some inks on, like some highlighter inks. I'm going to go for, let's say, some orange, say some green as well, and some of this purple here. Now what happens is, after we've put these inks on, these will travel some distance up the paper, because solvent goes onto the paper first, and then it carries these inks up some distance. And what happens is, if there are a mixture of inks inside the sample, these will then get separated along the way. So each component or ink in the mixture will travel a different distance. Now, if two different components or two different inks within a mixture travel the same distance, let's say eventually we have, let's say eventually some reds here and some reds here from the purple, you can tell that they're the same because they travel the same distance. Like this, right here. Now, one other thing you may need to be familiar with are RF values when you analyze some chromatograms. So these are used to identify the actual substance itself. So many substances will have an RF value which is stored in a database. So RF values are like how far they get carried up the chromatography paper. So it depends on how like far the solvent has traveled as well. So the RF value equals the distance traveled by the, let's say, the ink divided by the distance traveled by the solvent. For example, let's say we have a substance with an RF value of 0.36 and it's traveled 29 millimeters up a chromatogram, and we want to know how far the solvent travelled. So we substitute our values in. The distance travelled by the ink, which is 29 millimeters, divided by the solvent distance, which is unknown. So if we rearrange this, what we get is solvent equals the 29 divided by 0.36, which gets us about 80.5 or 80.6 millimeters. And I've done that to three significant figures. Now, however, the RF values will actually change depending on a few things that you use for chromatography. It depends on two things. It depends on the solvent you use, because the ink or substance gets attracted to the solvent. You could also link this to the solubility of the ink or substance, as in how much does it dissolve inside the solvent. You could also say the paper used as well, because the ink or substance is attracted to some extent to the paper. Now, I haven't actually done a chromatogram yet, but I can make a short video soon. This is where I'll do this slide right here, and then we'll give a few conclusions about, let's say, one of the ink style labeled B1. Now we move on to triple science only content. So this is testing for ions, so testing for the actual elements in a substance. One way you can identify an ion or a substance or an actual element could be for the flame tests. These are used to identify metals. So first, what we do is we clean a wooden splint or a metal loop, let's say with water, and then we dip its little tip into the compound, let's say an ionic one, and that's usually in a solution. Then what we do is we put the tip of the splint or the loop into a blue Bunsen burner flame, and then should turn the flame a different nice color, and we observe and record it. Simple as that. And remember, if you want to test for another substance, you'll need to clean the loop again and dip it so it doesn't contaminate. So you can easily say it's the different substance causing the different flame. Now you'll need to know the colors produced from different metals. So these are what you need to know. Sodium produces a yellow flame. Lithium produces a crimson red flame. Potassium produces a lilac or purple flame. Copper produces a green flame. And calcium produces an orange red flame. You'll just need to learn this. Now, another way you could test for metals or metal ions is by using sodium hydroxide solution. So this is where a precipitate is produced. So first, what we do is we just add 4 drops of sodium hydroxide into the test tube or the sample that we are doing or testing. Now, again, we've got some colors to memorize. So the metals such as calcium, magnesium, and aluminium turn white. Now, the only special one is aluminium. Now, this is where if we put more sodium hydroxide in, as in excess, the precipitates, which are like a white solid that's not soluble, it will redissolve again and turn colorless again. So basically, if it turns white and then colorless again, it's aluminium. Now, some other ones you need to know is a copper 2 ion is produces a blue precipitate. That's why compounds like copper sulfate produce like blue liquids and crystals. You should know that the iron 2 ion produces a green like precipitate, as an iron 3 ion will produce a brown precipitate. Just useful to know is that transition metals will produce a nice coloured precipitate. Otherwise, it's just white. That's one way to remember this. Now, a third way you could test for metal ions is something you wouldn't do at school. This is flame emissions spectroscopy. So this is where we try and identify a mixture of ions. Now, the other methods don't work well. That's even the flame test and the adding of sodium hydroxide solution. Now, they don't work because the colors can mix up together and what we call mask each other out. So one could appear more than the other. Let's say a green flame could appear over a lilac or purple flame. Now, instead, we still use like a flame test, but what we do is after the sample is heated, we put some film around it, and then depending on what wavelengths of light are released from that like sample, you'll see some lines come up. For example, like this. So wherever it matches up, it's present. For example, this strontium has these little wavelengths here, or colors that are produced, which from the sample are here, here, here. Basically if it matches up with some of the sample like this, that means this is in here. The strontium is in the sample. The other one is the titanium because it matches these ones here, as well as these. Now, the other ions you need to test for are negative or non-metal ions, or anions. Now, you need to know quite a few different tests here. So to test for halides, these are group 7, like ions such as chlorine, bromine, and iodine. Those are the three ones you actually need to know. What you need to do first is add a few drops of nitric acid, then a few drops of silver nitrate. So you need to know about these two chemicals that you add. Now, once you do this, let's say if there's chlorine present, it'll produce a white precipitate. If bromine is present, a cream precipitate is produced. And if iodide or an iodine is produced, a yellow precipitate is produced. I just like to remember this from the periodic table. So you have in the group Cl, then Br, then I. They just get more colourful as you go down. So you start with the white, then you go to cream, then yellow. Now, some other ways you could test for some negative ions are, such as for carbonates. So as you know from Unit 4 with the reactions with acids, carbonates, metal carbonates would react with acids to produce a salt, water, and carbon dioxide. So we would use or add some dilute hydrochloric acid to the sample in a test tube. Then we seal the test tube with a bung and delivery tube, and we feed that delivery tube into another test tube filled with lime water. So essentially we're seeing if carbon dioxide is produced. So if we have our first test tube, we have the sample, then we have the sealed delivery like bung, and then delivery tube right into this. Where if the lime water here turns cloudy, that means carbon dioxide is produced. That means there's carbonates inside the sample. The other ion you need to know to test for is sulfate ions. So first, we add 3 drops of dilute hydrochloric acid to make sure any carbon ions are reacted with, and then barium chloride solution. Now, if the sulfate ions are present, a white precipitate forms. Again, you'll just need to learn all these tests for triple science. Next is Unit 9, which is Chemistry of the Atmosphere. Now, you'll need to know about the composition of the atmosphere, as in what gases make up the atmosphere. After all, the atmosphere or air is just a mixture of gases. So we need to roughly describe the composition of the early and present atmosphere of the Earth. We need to give approximate percentages. For example, at the start it was mostly carbon dioxide, as in we only need to give approximate percentages for the modern atmosphere. How much of her money did she spend? How much of her money did she spend?
The total from them.
Yeah, but you already know she has 2/3 left, or how much did she spend as in thirds? There's 2/3 left, 1/3 was spent. Which is that?
By 2.
You gotta decide. So in the early atmosphere, it was mostly carbon dioxide, whereas now well, there isn't much. It's like there's barely any, so the 0.04%, something like that. With oxygen, there was barely like nothing or none, no oxygen in the early atmosphere, but now it makes up about 21% of the atmosphere. Another gas you need to know about is nitrogen. Again, there wasn't much nitrogen in the early atmosphere, but now it makes up most of the atmosphere, 78% of it. Whereas water vapor, there was still like lots of it in the early atmosphere, but much less now. Like less than like 0.1%, something like that. There's very little water vapor. Now, how did all these percentages of gases change over time from like millions of years ago to now? Now, this is often, let's say, quite a high mark question if it asks you altogether how it changed. Now, first, initially in the early atmosphere, there was lots of water vapor, carbon dioxide, some nitrogen, and quite a bit of methane as well. That was due to the volcanic activity. However, after this, the Earth started to cool down. So that meant the water vapor eventually condensed into liquid at its boiling point, about 100 degrees Celsius, and that formed the oceans. Now, as a result, some of the carbon dioxide also dissolved in the water, and more carbon dioxide dissolves at lower temperatures, and that's a useful thing you need to know. Eventually, some organisms started to develop, so these could carry out photosynthesis, which takes in carbon dioxide, which reduces the amount of carbon dioxide, and increase the amount of oxygen, as oxygen is produced from photosynthesis. That's your biology there. And then with even more organisms like being developed. Now, when these organisms died, these then fell to the bottom of the seabed and then was compressed from above. So that meant all the carbon stored in these organisms, as well as rocks as well, fell to the seabed, got compressed, and that means the carbon got locked up in things like fossils and carbonates. Now, combined foundations here need to look at atmospheric pollutants, as in these are issues today with the atmosphere. As you should know, when fuel is burnt or reacts with oxygen, it undergoes combustion, and it can usually gives out carbon dioxide and water as its products if there's enough oxygen. However, let's say when you burn stuff and you use air instead, because air is a mixture, you get other compounds being produced, such as nitrogen oxides, because there's nitrogen in the air which reacts with oxygen, and this can cause respiratory health problems. You also get sulfur dioxide. This causes acid rain, which can erode buildings and destroy environments, and can again cause respiratory health problems. And lastly, carbon monoxide could be produced. So this is toxic and also hard to detect because it's colorless and hard, odorless. And this is produced when there isn't enough oxygen. So that's when incomplete combustion is used. If there really isn't enough carbon, like oxygen, instead some carbon particulates or like soot can be produced. This again can cause respiratory health problems. Now that's the end of Unit 9, and we're moving on to the final unit, using resources. First, all tiers and groups need to know what's meant by potable water. This is water that is safe to drink. Now this is different to pure water because potable water contains like mineral ions, while pure water contains only water molecules, nothing else. Now, to get potable water that is safe to drink, we could use, let's say, some processes that treat ground or fresh water. Now, when we treat grounds or fresh water, we go through two main stages, which you should be familiar with. First is filtration. This removes insoluble solids from the water, things like twigs, dirt, rocks, and so on. Next, after this, all this filtered water then is sterilized. So this is to kill harmful bacteria. This is where we can use chemicals such as ozone or chlorine or even UV light. Another way you could obtain potable water or like drinkable water is through treating seawater. This is called desalination, where we simply remove the salt. Now, for both methods, we first start off with filtration again to remove again any insoluble solids, this time things like sands, rocks, and so on. One method of treating seawater is distillation. So this is where the seawater is simply heated and the water vapor is collected and then condensed into a container. The other method is reverse osmosis. So the seawater is pumped through a partially permeable membrane. So membrane that only lets water pass through the membrane. So that means everything else like salts and so on gets stuck behind. All you're left with is just water. Now, why don't we treat seawater? We don't treat seawater because it's more expensive. This is because if you look at what's underlined here, it requires lots of energy. If you use more energy or need more energy, it's more expensive. Now, the other water treatment you need to know is treating wastewater. Now, there are three stages to this. First is screening. So this is similar to filtration, where insoluble solids are removed. Things you'd find in sewage, such as plastics, and you'd use a wire mesh for this. Next is sedimentation. So this filtered water then sits in a large tank. So we have our filtered water entering here. Now, what happens is this is left for quite a long time. Then a sludge will collect at the bottom, whereas the liquid on top is called the effluent. Now, things happen to these. Like they go their separate ways. So afterwards, they're digested. So the effluent, the liquid on top, is digested by bacteria aerobically. So that's with air. Then afterwards, the effluent is then safe to release back into the environment. Whereas the sludge is then separated from the effluent and it's digested anaerobically. And then the remaining sludge can be used as fertilizers. Now, triple foundation need to have a required practical on testing the purity of water. This is likely to come up on the exam. Now, there are a few ways to check the purity of water. First is the pH of water. So use like a pH meter or universal indicator. Now, you should expect pure water to have a pH of 7.0. Now, the closer the pH is to 7.0, the more pure the sample of water is. Another way you could test for the purity of water is its boiling point. So pure water will boil at exactly 100 degrees Celsius. So that's when, when you start boiling some water, the temperature keeps rising until it stays flat for a bit. Now, the higher the boiling point is, the less pure the sample of water is. And lastly, the final way to test the purity of water is the actual required practical. So this is where we figure out the mass of dissolved solids in the sample. So first, we measure and record the mass of an empty evaporating dish with a top pan balance. Then you measure out 50 cubic centimeters of the sample of water into the evaporating dish, and you measure that volume with a measuring cylinder. Next, you heat the sample of water in the evaporating dish until all the water is evaporated. This just leaves the dissolved solids inside the evaporating dish. Afterwards, you measure the mass of the dish when all the water has evaporated on the top pan balance. Now, to calculate the mass of dissolved solids, you need to figure out or calculate the change in mass. So that's the mass of the water after everything has been evaporated minus the mass of the empty dish. Lastly, you calculate the concentration of dissolved solids by dividing by the volume of water. For example, let's say you had 2 grams of dissolved solids in 400 cubic centimeters of water. The concentration is your mass of dissolved solids divided by the volume, which is your 2 grams divided by your 400 cubic centimeters, which is 0.005 grams per cubic centimeter. Now, less pure samples of water will have a higher concentration of dissolved solids. So if you're testing for multiple samples of water, you could find the concentration of dissolved solids in each, and then you can place them in descending order. That gives you the least to highest purity of each sample. Now, going back to content for all groups and tiers, this is now using resources. You need to know what's meant by sustainability. This is where we can meet our own needs without compromising the needs of future generations. In other words, that means we shouldn't use up, let's say, a resource in a way that the next generation won't have enough of for themselves. You also need to know what's meant by a finite resource. So these are resources that are limited. These will run out. You also need to know what's meant by renewable resources. So these are resources that are unlikely to run out. In other words, they can also be replaced at the same rate they're used. One a good example could be trees, for example, or wood. After we cut down trees, we can replace them by planting. That can show it's renewable because we can replace all that wood that's been used up, and that means it's also sustainable because it's unlikely to run out and unlikely to run out for the future generations. So the future generations still have, let's say, access to all this wood. Now, we can make resources like more sustainably used. For example, we can use less of the resource to extend its life or reduce demand. We could also recycle or reuse materials, or we could simply make products last longer. This will just reduce the demand because we don't need to replace that products as often, and we don't need as many materials and energy like to produce that product. Now, as a quick note, some products use both natural and synthetic materials, as in both renewable and non-renewable materials. For example, like carpets having both wool, which is renewable, and polystyrene, which is made from crude oil. And that's because the product is made longer and makes both resources sustainable. Now, one special case is for higher tier. They'll need to know about sustainable, like production of copper or obtaining copper in a sustainable way. So copper used to be obtained from high-grade ores, so these are ones with a high percentage mass of copper. The metal itself was obtained by reduction with carbon. So as in the carbon would react with the oxygen in the ore and just leave the copper by itself. Now, for reduction to happen, you need high temperatures, and that's why this took place often in a blast furnace. This needs lots of energy. That means this is actually a high cost as well, and that means lots of copper must be produced to offset this. So you need enough copper in the ore to make it worthwhile to use this. This traditional method also brought out some problems. It's not sustainable because the high supply of high grade ores are running out. And again, this process doesn't work well on low grade ores because the reduction requires lots of energy to the high temperatures. If you use low grade ores, you won't get as much copper from the low grade ores, and therefore you'll make less money or even be at a loss. Another point as well is that the carbon often comes from coal, another finite resource, and that since the carbon reacts with oxygen, it often produces either carbon monoxide or carbon dioxide, which again contributes to global warming. So that's why we've had to switch to alternative methods of obtaining copper, one of which was phytomining. So this is where the low-grade copper ores are mixed with the soil of plants. Now over time the plants will absorb the copper in the leaves and then produce soluble copper compounds. After some time the plants can then be burnt and then have their ashes collected. That will contain copper compounds. Then these copper compounds can be dissolved in water, and then we can use electrolysis to obtain the copper, or use scrap iron in a displacement reaction that just leaves the copper on its own. The other method was bioleaching, so that's where bacteria convert these copper compounds into low-grade ores into soluble copper compounds. And then the last step is the same again. These compounds can be dissolved, and then copper can be extracted by electrolysis or displacement with scrap iron. Now, these methods aren't used as much still because, firstly, they're slow, and that means they're less profitable. And if they're slow as well, you could argue that they're more expensive. And lastly, another part of these using resources is life cycle assessments, mainly for triple foundation. Now, if we wanted to look at the environmental impact of a product, or even compare it with others, we can look at its, let's say, the carbon footprint, that's its CO2 equivalent emissions, it's the sustainability of materials that's used, such as, let's say, for if it uses plastic or other materials like wood, as well as, let's say, the energy used in, let's say, manufacturing and transport and so on. Now, each will vary depending on the product at each stage of its life, and it makes it even easier to compare. And you need to know the 4 stages at which they're compared. First, you need to compare at the acquisition of materials, so that's where the materials are obtained. Next is the manufacturing. This looks more at energy. Next is the use and reuse. For example, does it have a carbon footprint when it's used? One notable example could be cars or boilers. Can it be reused every time? And lastly is disposal at the end. Does it, let's say, have an impact on the environment around, such as at landfill when it's disposed? Now, some other notes for LCAs or life cycle assessments are here. So these are often evaluate questions. These are 6 markers where you evaluate the environmental impacts of a product at each of its stages. For example, at stage 1, where you get the raw materials, is the material sustainable, like wood? Is it finite? Does it use, let's say, crude oil? Is it renewable? Does it even, let's say, use recycled materials? Now at manufacturing, step 2 or stage 2, how much energy is needed to manufacture the product? Is there any pollution or waste produced from it? If there's any waste or, let's say, other products, are they useful? Next is the use and reuse. For example, how heavy is it for transport? Because if it's heavier, it needs more energy to transport, and often that will have a larger carbon footprint because more energy is needed by those that transport it, let's say the trucks, airplanes, and so on. Now, during its actual use by the user, does it cause CO2 emissions or other pollutants? How long is its lifespan, perhaps? Because if you have a longer lifespan, all of these like impacts get spread over its lifetime. And lastly, at disposal, does the product decompose? Can any chemical it use leak into the environment? For the first one, let's say things like paper will decompose. You could see them as like biodegradable materials. And for the second question, this is quite notable with, let's say, batteries. Batteries will contain chemicals that can leak into the environment. And remember, at the end, after all this, you'll need to have a justified conclusion, as in which product you prefer. Now, you may get a follow-up question as well, such as the limitations of LCAs. Now, the limitation is that they're not peer-reviewed, as in seen by other people. This is because they're carried out by only one person. This can mean claims are somewhat biased or even false or misleading. And lastly for tonight is for triple only, or triple science only. It's the Haber process. So that's where we produce ammonia. So the Haber process reaction was used in our example for the reversible reaction. So we've got some further notes. The side that the equilibrium shifts to will have a higher yield, so more reactants or more products. And remember, we want to make more products, more ammonia. Now, the Haber process uses these two conditions which you need to learn. A temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and that's it. Now, we need to discuss what effect of each condition does on the equilibrium. So like what happens to the equilibrium? Which way does it shift? And even then, we need to ask why these specific conditions are used. For example, 450 degrees Celsius is a high temperature. And remember that the forward reaction is exothermic, and the backward reaction is endothermic. So if we've got a high temperature, that means the system will counteract by decreasing the temperature. That means the endothermic reaction happens faster. Oh, and it's gone off for some reason. Right, I'll continue actually. Right, so continuing where we were. So we saw that, right, continuing where we were, we saw the endothermic reaction happens faster, so the equilibrium shifts actually to the left. So it actually decreases the yield of the products. Now this condition is still used because high temperature also means a higher rate of reaction. Now the other condition is the high pressure, the 200 atmospheres. So that's the high pressure. So the system counteracts by decreasing the pressure. That means there's to the side with fewer molecules. It means the equilibrium shifts to the right. And also the high pressure causes a faster rate of reaction as well. However, we can't go like any higher than this because higher pressures are more expensive. Now, overall, that's actually it for paper 2 of chemistry, and good luck on your exams.